stability means the aircraft has a tendency to return to its equilibrium. Within a bracket, equilibrium means here straight and level flight. Straight and level flight. If the aircraft was disrupted during flight, for example, by a crosswind or whatever, so we say stability. This aircraft has a positive stability, which means the aircraft can return to its equilibrium, straight and level flight, by itself, without any intervene from the pilot. Then we can say that stability, it is a manufacturer design. So this aircraft has been designed to have a stability, and the stability could be either positive, negative, or a neutral. Positive, negative, or a neutral. Now, if we say a static stability, and there's some other terms, another term that is called a dynamic stability. Now the difference between them, static stability is the ability of the aircraft to move or to turn, but the dynamic stability is the time required by the aircraft to respond to its static stability. So if this aircraft has been designed with a positive static stability, means the aircraft, if disrupted, will correct itself. Aircraft, for example, was flying straight and level flight. For any sudden movement happen, like a crosswind, for example, goes like this, then by itself, without any movement or any intervention from the pilot, will correct itself back in the same position. So if the aircraft comes back to its same position, means this aircraft has been designed with a positive static stability. A different type of static stability that is called a neutral static stability. It is the ability of the aircraft to correct itself, but instead of coming back to its original position where it has been disrupted, it will be able to correct itself in the new position. For example, flying straight and level flight, then for any sudden things happen, move like this, then aircraft was able by itself to correct itself here again and keep on flying stable. So a neutral is the ability of the aircraft to return or to correct itself in its new position. Now, the third term is called a negative aircraft stability. This aircraft has been designed with a negative stability, static stability, which means if the aircraft for any certain reason has been disrupted during flight, will not be able to correct itself unless the pilot intervene. So now we know the difference between positive static stability and neutral static stability and negative static stability. Now, a dynamic stability also could be positive, neutral, or negative. And as we have defined it a while ago, it is the time required. How much time does the aircraft need to correct itself or to respond to its designed stability? One of the three we have mentioned a while ago. Now, a certain movement, let's go for another subject. A certain movement might occur or happen to the aircraft during flight, which is not intentionally has been made or done by the pilot. Like a movement is being called adverse yaw. Adverse yaw. Now, adverse yaw, if you just want to define it, we say adverse yaw is the ability of the aircraft nose to go outside the turn. Aircraft is turning, for example, to the right, turning, then there is something trying to force the aircraft nose to go outside the turn. If it turns to this way, it is a certain force that tries to take this aircraft nose outside of the turn. This is, of course, by centripetal and centrifugal force. Centripetal and centrifugal force. What the manufacturer done, what did they have done in order to come out or to counteract this problem? They have, within the design itself, or the component has been installed in the aircraft. For example, let's first know that there is two different ways of coming out from this problem. There is two different ways. It is either by having an interconnection between the movement of the aileron and the rudder. Movement between the aileron and the rudder. For example, aircraft is turning to the right, I will have the rudder deflected at the same time. By the movement, if I want to move the aircraft to the right, for example, how will I move it? How will I move it?
By aileron?
It is by
By
the yoke. It is by using the flight control, which is called the aircraft aileron. Am I right? So, for example, the downgoing wing, if I'm turning to the right, I will be having a downgoing wing and upgoing wing. And we know the downgoing wing will always have what we call an upgoing aileron. An upgoing aileron. While the upgoing from the other side has a downgoing aileron. So, if we choose that to have this such design on the aircraft to counteract the adverse yaw by the interconnecting between aileron, the movement of the aileron, and the rudder, for example, if the aircraft moves to the right, this aileron goes up, the other one goes down. At the same time, I will have, because of the interconnecting rods between the aileron and the rudder, I have the rudder will be moved to this direction.
in the same time?
Or to the other direction.
In the
To
same
which
time.
direction will go? To which direction? The same direction of the
Same.
upgoing aileron.
Uh-huh.
It will go to the same direction of the upgoing aileron. This aileron goes up, this rudder will be deflected slightly. The movement degree, that is what?
What is it?
Enough to compensate this adverse yaw movement. The movement degree that is enough to compensate what we call the adverse yaw movement. So by moving the rudder to this direction, then I'm forcing the tail to stay in this direction. At the same time, I'm forcing the nose to sustain in the same direction of the turning. Am I right? The other solution they have made is by using a special design of an aileron. Because you know that this movement, we have an aileron movement. Aileron control surface has to be moved in order to have the turning movement. Am I right? That we all know. So I did install a special design of that aileron, which is called a Fry's aileron. Let's just continue. What is this? Function F3. So, as of what I was saying a while ago, that's verse yaw, as it's mentioned here on my slideshow, says that it's the tendency of the aircraft nose to go outside the turret. Outside the turret. And we given two solutions for this, in order to counteract this problem. The first one was by an interconnecting between the movement of the aileron as well as the rudder. The second one we were talking about is by using a special design of an aileron that is called a Fry's aileron. A Fry's aileron is the type which is the type most commonly used today to minimize what we call the aileron drag because of the location of its hinge point. then I'm playing with the hinge point. I'm playing with the hinge point of the aileron. Now, the hinge point of the aileron. Do we have a mic? Now, where is the location of the flight control that is called aileron? Can tell me. On the wing.
On the
But
wing.
this is not enough. It is on the wing, but this is not enough. Trailing edge. Still, it is not enough. Where is the location? The outboard portion, right? Closer to the tip. Closer to the tip, because the wing, we have root and we have tip, right?
Yeah.
So, if we go, for example, to the wing, this is the wing, right? This is the wing. If we have, this is the root. Here is the tip. Here we have another flight control that's written here, which is called the hydrophone passage, which is flat. So this is the aileron. Okay? Aileron. This is the aileron. It is located. This is leading edge, trailing edge, right? Here, inner portion. This is the outer portion. So the equation of the aileron, it is available on the trailing edge, outer portion, closer to the wing tip. Now, we said the other procedure, the other way for counteracting what we call the adversarial problem was by having a special or a most commonly used lower aileron that is installed on the aircraft. Now, if we look to the aerofoil section or to the actual wing, we see that this is, for example, the wing. The aileron is located somewhere here. Okay? Now, this is when it is in neutral. It looks this way. If you look to the wing, if you take what we call a section view and look to the aircraft wing, you will see that this is the wing and the aileron is attached at the trailing edge here, and when it is in neutral, it looks this way. Normally, the other different types of ailerons, if it is moved, let's first draw a normal aileron installed in the aircraft and not a fries aileron. So the normal aileron will be, okay, this is 1, 2, 3. Now if the aileron moves up, okay, this is neutral. If it moves up, like this, if it moves down, like this. This is a normal aileron. This is a normal aileron. But in order to counteract what we call an adverse yaw, we have installed a different type of aileron that is called the fries aileron. Let's see the difference in movement. The difference in movement. This is in neutral, okay? Now, a fries aileron. This is an up movement. This is a down movement of the aileron. So, which means, if you notice, the outgoing aileron will have a protrusion of the aileron beneath the aircraft wing. What will this thing do? If you remember, yes, if you remember, we said that in the other solution, the previous solution, that when the aileron moved, in order to turn the aircraft, the outgoing aileron, the downgoing wing, will have the rudder deflected in that direction. So we'll have a force trying to keep the nose steady, right? Which means because of the deflection here. In order to counteract what? To counteract the difference of lift, which is the drag that being made on the aircraft, because the drag sometimes it is increased whenever the lift is increased. Remember the type of drags? The type of drag says that we have something called induced drag. And the induced drag was due to the increase of lift. Whenever aircraft lift is increased, the drag is also increased. So here, what happens? Why do we have adverse yaw? Now I have a downgoing aileron, upgoing wing here because the aileron was deflected down. I have more lift here, I have more induced drag. So the aircraft tries to go like this. So, which means it is because of the drag created on the downgoing aileron, right? So, if I made this aileron comes down a little bit beneath the aircraft wing, which means I'm creating a drag here. I'm creating a drag here, compensating the drag that comes on the other wing. That's how I keep the aircraft nose in the turn and not to try to go out, which is called an adverse yaw. So this is the upgoing aileron. I have a protrusion here. I have an airstream. This airstream hits the aileron from here, creating a drag. Creating a drag. So, adverse yaw, it is the tendency of the aircraft nose to return, to go outside of its turn. How we did solve this problem? We solve it by one of two means. Either by interconnecting between aileron and rudder as a movement. Talking, whenever that moves, this one moves in the same direction, or by having a most commonly used aileron nowadays, which is called a Fry's aileron. Any question, guys?
Thank you.
Thank you very much.
Thank you.